Today, we're going to take a journey. It starts somewhere you probably remember pretty well, high school algebra, but it ends up in a place so advanced, it kind of rewrites the rules of math itself. Okay, let's get into it.
Yeah, you remember this, right? Breaking down those, pesky polynomials into smaller, bite-sized pieces. You just stare at the equation, trying to figure out the magic combination of numbers that would solve the puzzle. It really felt like a neat little trick, just a set of rules you had to learn.
And that's exactly where we're going to kick things off. This quote from the iTutor guide just perfectly captures that feeling of, yeah, I got this, once you know the steps. So let's do a quick warm-up, get those math muscles going again. So we're going to use a method that iTutor calls, and I love this, the killer method. It's a really simple 5-step process for cracking open those standard quadratic trinomials. See? It's basically a recipe. You identify your ingredients, that's A, B, and C. You find the biggest thing they all have in common, the greatest common factor. You pull that out, solve the easier puzzle that's left over, and then you just write down your final answer. Let's see how it works. Okay, here's our practice problem pulled straight from the guide. We've got a 6 for our A, a 15 for our B, and a 9 for our C. Now let's just run the steps.
Step 2 is finding that GCF. So what's the largest number that divides evenly into 6, 15, and 9? You think about it for a second, and yeah, it's 3. Simple enough.
All right, step 3. We just pull that 3 right out front. So 6x squared divided by 3 gives you 2x squared. 15x divided by 3 is 5x. And 9 divided by 3, well, that's 3. And just like that, the problem inside the parentheses looks way less intimidating. For the last couple steps, we just have to tackle that smaller piece. We're looking for 2 things that multiply to 6 and add up to 5. A little bit of trial and error, and you land on 2x plus 3 and x plus 1. We stick the 3 back on the front, and we have our answer. And there you go. A neat, tidy solution to a problem that felt totally predictable. You follow the rules, you get the right answer. It's comforting, really. But what happens if the rules themselves just change? Whoa, okay? This is not your high school textbook anymore. This is the title page of a master's thesis. General factoring algorithms for polynomials over finite fields. Suddenly, factoring doesn't feel so simple, does it? We've just jumped out of the kiddie pool and straight into the deep end of the ocean. To even begin to wrap our heads around what's going on here, we have to throw out some of our most basic ideas about how numbers even work. We're about to step into a completely new mathematical universe. The key phrase on that page is finite fields. I mean, what on earth does that even mean? It sounds super complicated, but there's actually a pretty simple way to think about it. Just imagine a clock. When the hour hand gets to 12, what happens next? It doesn't go to 13, right? It wraps back around to 1. Well, that's the basic idea of a finite field. It's a number system that has a limited number of elements and just loops back on itself. So in a clock with only 5 numbers, 4 plus 2 wouldn't be 6, it would be 1. Wild, right? And this has a huge implication. Here's the kicker. The familiar rules for factoring, the ones that worked so perfectly for us just a minute ago, they might not apply at all in these weird new number systems. All of a sudden, solving a polynomial becomes a fundamentally harder problem. And that is the grand challenge that mathematicians decided to take on. This quote from the thesis abstract lays it all out. Their goal was to create a kind of master key, a set of rules that could factor any polynomial, no matter which strange clock-like universe it happened to live in. Now, this wasn't the work of just one person. It was really a journey of discovery, with each new idea building on the one before it. Let's meet a couple of the key players. Our story really kicks into high gear in 1967. A mathematician named Elwin Berlekamp was the first person to come up with an efficient, reliable method to crack this exact problem. He really laid the foundation for everything that came after. And his work wasn't just groundbreaking, it was beautiful. As the thesis puts it, it was both unbelievably clever and very accessible. It was just this elegant solution that opened a door for everyone else to walk through. And that's exactly what happened. In 1981, inspired by Berlekamp's amazing breakthrough, 2 other mathematicians, David Cantor and Hans Zassenhaus, developed their own method. And that's how progress in math so often works. One brilliant idea sparks the next one. So at this point, you might be thinking, Okay, that's pretty clever, I guess. But why should I care? I mean, clock arithmetic and finite fields sound pretty disconnected from our everyday lives. But this abstract stuff has some seriously profound implications.
Look, this isn't just about solving some niche puzzle for mathematicians. It's about forging universal tools. These algorithms are actually the foundation for things like modern cryptography, the stuff that keeps all your online information safe. Every single time you send a secure message or buy something online, you are relying on the kind of high-level math that grew from these very ideas. So what started out as a simple set of rules for solving a high school algebra problem just blossoms into this incredibly deep and complex field of study. It just goes to show you that even the most basic things we learn in math can hide entire universes of complexity just waiting there for us to explore.
And that really leaves us with one final thought. We just saw how a simple idea like factoring can explode in complexity just by changing the number system you're working in. It really makes you wonder, doesn't it? What other simple problems from school are actually just the tiny, visible tip of a massive hidden iceberg?